All right, so let's look at experiment number 10. And so in this particular experiment and subsequent ones, we will look at design and simulation of digital circuits. So in this particular lab number 10, what we'll do is we'll start with simulating some very basic circuits, starting with basic gates. And then we'll look at design of a full adder, and then simulating it in microcap simulator to check that the design is correct. And then we'll look at use of 7-segment displays and A to D converters, where what we would do is we would take an analog voltage, convert it into a digital output, and then display it on a 7-segment display here. All right, so let's open up the simulator and look at how we are going to do all these parts of the experiment here. All right, so this is our microcap simulator. And in the microcap simulator, just like the basic elements such as diodes and transistors and resistors, we have basic gates also. So for example, if you go and look at here, there is something called standard gates in digital primitives. There's something called standard gates here. And you could select any of those gates. For example, you could select AND gates, and there's a 2-input AND gate, 3-input AND gate, and so on and so forth. And then there are, for example, NAND gates are there, NOR gates are there, OR gate, XOR, and all the basic gates are there here. So you could select, for example, in this case, I've selected a basic XOR gate here. All right, XOR gate has been selected. So that's the first thing that you do is select a gate. And then you have to apply inputs to the gates here. So these are the inputs here, right? So this is an input here to the gate. And the way you do that is by going and looking at stimulus. So stimulus generators are the inputs to the digital gates here. And fixed digital is you can apply only a 1 or a 0 here. So that's a fixed digital here. So that's what I've applied in this particular case here, a fixed digital input here. These two here, right? So you can apply an input to any of these gates, fixed digital inputs, and you can vary the value by double clicking on it. You can make it 1, you can make both of them 1, and things like that here. And so we can simulate the circuit now. So we can do a dynamic DC here. So it tells us that when we apply 1 and 1, the output of the XOR gate is 0, which is correct. So we can change this input here to 0 and 1 and 0, so it becomes 1 here. We can make the other one, let's say other one also 0. So it becomes 0, 0, so it's expected. So when you apply 0, 0 is 0 here. And, and like that you can vary, make both of them 1 and right, so make both of them 1. So like that you can verify the truth table of the basic gates here. So you can select any of these gates that you see here, AND gates, NAND gates, NOR gates, and you can apply this fixed stimulus. This is called a fixed stimulus here, and you can apply that, and you can check the basic output here, right? What you can also do is you can take a let's get out of it here. You can take a NAND gate here. So in this case, I've taken a NAND gate. I've applied a fixed stimulus one here, and I've applied a time varying stimulus here. So what you can do is, for example, you can go in stimulus generator and you can select a 1-bit stimulus here, right? So this is the 1-bit stimulus here. So this is what I've applied here. And when you go into 1-bit stimulus here, what we have done is we have applied that to start with, we have a 0. Then after 15 nanoseconds, it goes to 1. And after 100 nanoseconds, it goes to 0 here. So you can define the way your waveform looks like here. All right, don't look at this define 100 megahertz clock. Those are some default waveforms. So you can define after any, for example, after 150 nanoseconds, I can make it 1 again and things like that. So we can define a waveform, a 1-bit waveform through this particular means here. And note that these gates that are there here, if you double click, what we have given these particular gates is a basic model of is shown here. So this is basically a delay model. All gates have delays. So the basic delay of our gate is here 1 nanosecond. High to low delay means that when the output goes from high to low, right? So you high to low, then the delay in the gate is 1 nanosecond. When the output goes from low to high, the delay is 1 nanosecond. These delays can be different depending on the design of the gates here. And these are, the delays are not a fixed quantity. They vary depending on various conditions. So what we are saying is that the minimum delay is 0.9 nanosecond. The maximum delay could be 1.1 nanosecond, and the average delay or the typical delay is 1 nanosecond here, right? So each of our gates has a delay of 1 nanosecond. That's how we have taken it here. So anyway, we have applied a fixed input of 1 to one of the inputs, and we have applied a stimulus, a time varying stimulus, and we can do a dynamic simulation here, or a transient simulation here. So when you do a transient simulation, so we are looking at so we are simulating it for 200 nanosecond, and the usual thing, operating point, auto scale range, and all that. So here, when you come here, what we are plotting is the digital value of input A. So go back and see. So what I've done is that each one of these lines, we have given it a label. So you can give a label by going to this text mode and attach a label at any of these wires here, okay? So we have given it a label A, and we have given it a label Y1. So that makes it easier for us, instead of looking at node numbers and all that. That makes it easy for us to identify. So this is input A and this is Y1 here. So what we are going to look at is transient limits. We're going to look at the digital value D of A and digital value of Y1, which is the output, right? And let's run it here. So this is what it shows. This is our input. So at 50 nanosecond, we made it 1, and after 100 nanosecond, we made it 0 here. And this is the output of the NAND gate here. So the NAND gate, you can see it is, the value is here. The value, for example, we can go and cursor. We can look at here, cursor here, right? So the NAND gate is 1 here. And then the NAND gate goes 0 here. So you can see how the value of the NAND gate changes here, right? Okay. All right, so you can do transient simulation, and you can look at the digital value of any of these lines that are there, and thereby look at how the circuit is performing in the time domain here. All right, so that's basically learning how to use microcap to simulate basic gates by applying a fixed digital input, or by applying a time varying input here. And you can define the nature of the time varying input through a simple set of commands that are given over here. All right, so next what we are going to do is basically design, now using these basic gates, design a full adder here. So full adder takes 3 inputs, A, B, and C here. There are 3 inputs here, and generates a sum bit and a carry bit here. And this is the truth table that is given over here. And from this truth table, we can write down the Boolean expression for the sum and the Boolean expression for the carry out. And then we can implement these sum and the carry out using basic gates. So that's what I've done here. So basically, this is the sum part here, and this is what is generating carry. And the 3 inputs that I have is A0, B0, and C0 here, right? So these are the 3 inputs that are there. And connecting wires and all that will become difficult, so it's best to again define a label for each one of these wires. So for example, I've called it C0, A0, and B0. And then when you go to any of these other inputs and you call it A0, it will automatically connect it to this particular one here. So that makes a diagram neat. Otherwise, we'll have a lot of wires crossing each other, and it may become difficult to make the circuit here. So the best thing is to label each one of these inputs, and whichever input is connected in common with others, you label them accordingly here. So we can see that this is our sum and carry here. So again, we can do dynamic DC here. Okay, so what we have done is We've applied a 1 here and a 1 here and a 0 here. So 1, 1. So the sum bit is 0 and the carry bit is 1 here. And if we apply, let's say 1 here also, then the sum bit is also 1 and the carry bit is also 1 here, right? So thereby you can verify, you can, after you do a combinational circuit design and implement it using gates, so you can then go ahead and check whether your design is correct or not by simulating it in this particular manner here. By applying this fixed stimulus here and using the basic gates from the library, you can construct the circuit here. All right, so in the next part, what we are going to look at is there is a device called a 7-segment display here. And so let me illustrate what this 7-segment display is there. So 7-segment display, you can go ahead and select from, let's see, stimulus here. We can go here, animation. Right, so if you go to animation, so you have this animated 7-segment display here, right? So you can choose this here from here. All right, so I've already chosen the 7-segment display, and there are 7 segments as you will see here, and they're 7 LEDs basically, and they're driven by these 7 inputs that are there here. So for example, if I make this 1, so it makes this particular LED lights up. Then I make the next one 1 here. Then this particular LED lights up. Then I make this one 1 here. So you can see here, this one lights up. So thereby we have now displayed a 7. Now let's put this one here. So this is this one here. Right. So this is now here. All right. And finally this one. So we've created a 0. And the middle one is this one here, right? So we have written an 8 here. So we can display any digit here. We can display a 1 or a 2 or a 3 or a 4 or a 5 by applying appropriate values to these particular inputs here. So it's very convenient, you know, when you have various digital signals in your circuit, you want to see what their value is. So instead of probing individually each particular line and checking whether it's 1 or 0, you can connect these 7 of them, these lines into a 7-segment display and see what the values are, right? So you can take a 7-segment display, apply and see here. So now, for example, if you would like to display a 2, so if you would like to display a 2 here, so this LED has to be on, so the first one has to be on, the second one has to be on, the last one has to be on, and then this one has to be on, and then this one has to be on, right? So appropriately see how you can apply these various inputs that are here to display a 2 or a 3 or a 4 and things like that here. So you can play around with this particular one. Now applying individually the various inputs that you see here, 1 and 1, and you know, it becomes a bit tedious. So what we can do is we also, instead of having a fixed stimulus like this 1-bit stimulus, we also have, you know, when you go back to the stimulus generator, so we have here a 8-bit stimulus here, right? So it can generate 8 bits simultaneously, right? So you can use an 8-bit stimulus. So that's what I've used here. So that makes it easy to generate the values here. So for example, when you double click on 8-bit stimulus, so you can write the value here in terms of hexadecimal, right? So hexadecimal here, it shows the number which is there here. So if it is 10 here, then you write A and B and C, D and all that, and so on and so forth. So I've applied 6D here, and so it generates these values here that you see, and it is connected here. So this A0 here, the same A0 label is attached here. So these are connected. So we get 5 here. So for example, all right, so let's go back here. So here, so we can apply here, let's say 6F, for example, right? So 6F generates a 9 here, right? So it's easy for us to, you know, by using a 8-bit stimulus generator and by putting an appropriate value here, it becomes easier to generate all these different bits. So instead of going and changing the value of each particular one that we were doing here, this makes it easier to drive a whole set of lines that are there here. But note that to generate a 9 or a 7 or a 6, we have to figure out what the appropriate values of each one of these lines are there, and then go ahead and program it, and that makes it a bit cumbersome. So an IC has been developed which will allow you to generate appropriate values. So if you want to generate a 7, so it would generate appropriate values of these voltages here. So let me show you here. So this is this particular IC, 74LS48 here. So this particular IC exists, is available, and note that it has 7 outputs here. The 7 outputs are connected to the 7 inputs of the 7-segment display. And now we don't really have to worry about which segment has to be on and off and all that to display a 5. All you need to do is you apply, this is the most significant bit and this is the least significant bit. So 5 we know is 1010. That's equal to 5, and so we have 5 displayed here. If I put a 111 here, so we get a 7 here. If I put a 0 here, I get a 6 here. This is 1106 here. And if I put a 0 here and a 0 here, we get a 0 here. If I put a 1 here, I get an 8 here. And if I put a 1 here, and I get a 9 here. So you can see that this particular IC makes it easy for us to use a 7-segment display to display the digital value of the binary input that we have here. If it is a 9, we get a 9. If we have an 8, we get an 8. And so that this IC makes our life easier to display to monitor the value of these particular lines here. All right, so 7-segment display is very convenient to monitor, to display the signals that we have in digital circuits. In the next part, what we are doing is we are basically looking at an A to D converter. So our goal is to use this 7-segment display that is there here, and we have an A to D converter. And what we would like to do is, whatever is the analog input, say if it is 2 analog input, 2 volt, we would like to display it as 2 volt here. If it is 3, we would like to see it as a 3 volt here. So it's basically like, you can think of it as a digital voltmeter. And so if it is 4, we would like to see 4 here. So that's what we intend to do. So we can use a from our, if you go here, you have A to D converters are available, and there are various kinds of A to D converters. So we've used a 4-bit A to D converter here, right? So 4-bit A to D converter here, that's what we've used. Okay, and so this 4-bit A to D converter, there are several things here. One is you have to define a reference voltage. So we've defined a reference voltage of 16. You'll see in a minute why we have done that, 16 here. Then this is where we apply the analog input in the in part here. And the conversion starts when you go from 0 to 1 here, right? So, or you go from 1 to 0 here. So we've applied a stimulus here. It will only convert the analog into a digital after it gets a appropriate input at the convert part here, right? So we've applied a stimulus, 1-bit stimulus here. So what we do is we go from we go from 0 to 1, and then from 1 to 0 here, right? So we create a 1 to 0 here signal here, and that causes the conversion to start, and it generates an appropriate value here at this particular place here. Now to do the to make the circuit work, you'll have to do a dynamic simulation. So the digital output is created here. So corresponding to this analog input, a digital output is created here, and this digital output, we feed it into our same 7-segment driver, and the 7-segment is here where we want to see what the output is here. All right, so let's do the transient simulation. So just run the transient simulation here and go back to the basic circuit here. Okay, so we have 0.6, it generates a 1. Note that if I put a 0.4 here, generates a 0 here. If I put a 2 volt here, it generates a 2. If I put a 3 here, it shows me 3 here. If I put a 7 here, it shows me 7 here. Put 11 here. Well, 11 it cannot show because we don't have a 2-bit 7-segment display here. So it will show us properly till 9 here. Right. So the 7-segment display along with the A to D converter here. So it takes a analog input, converts it to a digital value, and this digital value then we display on our 7-segment display here. So this analog to digital converter, this is what it basically does. So here we have shown you a 3-bit ADC here. So if it's a 3-bit ADC, so each bit corresponds to 1 by 2 to the power 3 here. So 3 by 1 over 2 to the power 3, which is 8 here. So this is how the A to D converter works here. And you can see here, if the input signal lies between 0 to 0.5, you get 0, 0, 0. 0.5 to 1.5, you get 1, and then so on and so forth here. Right, so you get 8, because it's a 3-bit A to D converter, so you get 8 possible digital values here, from 0, 0, 0 to 1, 1, 1 here. And this is how the mapping is done here. Right, and so in our case, we are using a 4-bit A to D converter, and so that's where we have chosen vref equal to 16, and then a similar mapping is done here. From 0 to 0 0.5, it gives us a 4-bit output 0, 0, 0, 0. From 0.5 to 1.5, it gives us a 4-bit output here, right? And so this is the part where we use A to D converter along with a 7-segment driver and a 7-segment display to see the output that we have here. If you're interested, what you can do is, in the last experiment we had done a thermometer. So you can take the output of the thermometer, the analog output that is there from the thermometer, use a A to D converter, and then it becomes a bit complicated, A to D converter, and then you can use 2 7-segment displays to show the temperature, whether the temperature is 25 or 26 or 28. So it's a little bit complicated, but with the concepts that we have used in this particular lab, we have studied in this particular lab, you should be able to take a analog circuit, the output of the analog circuit, and then use A to D converters and this particular approach to display the value of the analog signal that is there here. All right, so we'll see more of digital circuits in the next lab. So let's stop here.